So I wanted to touch back on these notes a little bit to talk about the ionic strength and just to answer any questions that may have come up as we've looked at these. We talked about the need for activities, and essentially they're corrections for the equilibrium constant expression. And then there's some properties that you have to calculate to take these into account. And the most important one, I guess, or foundational one that you need to calculate is the ionic strength. Now, if you look at this reaction here, this is obviously the solubility product constant for barium sulfate. So barium sulfate, you have barium ions and sulfate ions, okay? Well, what we're saying about ionic strength and about these activities is the equilibrium of this particular reaction is affected by sodium chloride or any other kind of salt in solution. But sodium chloride doesn't play a role in this reaction. So how does it affect it? It affects it through these activity coefficients. So the stability of these ions in solution is affected by other ions in solution who don't participate in the reaction at all. So isn't that strange? Why would barium sulfate be affected by sodium or chloride? It's the stability of the aqueous solution. That's what's affecting the equilibrium. So we have to calculate the ionic strength. And so in this case, we have 4 different types of ions in solution. And so we're using this equation here. And so it's pretty straightforward. Notice we have the concentration of the species here. Find the pen. Right here. So this is the concentration of the species. So that's given right there, like the barium concentration. And then this Zi, that's the charge. And they're squared, so you really don't have to worry about pluses or minuses. Like if it's a negative charge or positive charge, it's the same. So notice how this is a sulfate, -2, but it's essentially it's -2 squared, right? So it doesn't matter what charge it is. So we're just saying that in aqueous solution, negative charges and positive charges have the same kind of effect, and it's related to the charge squared. Okay. Same with chloride over here, we have -1 squared, right, inside there, and then sodium. So notice the effect on the ionic strength is squared for multiple charges, like 2+, 2-. Aluminum has a huge effect on the ionic strength because it's 3+. Phosphate, 3+. So the more charge you have on the ion, it's a squared effect in terms of the ionic strength. And that's that entourage effect. It's creating multiple shells of organized water around it. So that's how you calculate the ionic strength. Now notice all of these things come in pairs. If I have positive ions, I have to have negative ions. And so that's what the 1/2 is sort of taken into consideration. We have sort of a double effect. They come in pairs, and so we're dividing that by 2. So that's the ionic strength. The ionic strength is used in calculating these coefficients, these thermodynamic coefficients. And you can see that these the more charge on the species, the more impact it has on the activity coefficients over here. So we have this debye-hukel equation, and you see ionic strength is a really important part of it. So right here. So you have to calculate mu first. And then once you have that, then you can look up this alpha I. That's that effective diameter of the hydrated ion in nanometers. And that's that entourage, that effective diameter in water. So if you have an aluminum 3+, it's going to have a huge ball of organized water around it. And they're going to go together. And if you have a tiny little potassium single charge, it's going to have a smaller ball of organized water around it. So it's the organized ball of water that we're really calculating here. It's not how big the ion is or how big the atom is. Okay. Now we've got some funny business constants in here, and it's just for aqueous solutions at 25C. So we're not deriving the equations in this section, but we've got these various constants in here that are for this calculation. Now all I've done for the equation on the left and right over here was a log of gamma. Here gamma, so I just raised both sides to 10 and I put the negative sign in there. So if you want to calculate the activity coefficient for a particular concentration, the concentrations are in the ionic string of a particular ion, which has a particular entourage hydrodynamic radius, and that ion has a particular charge, Zi, then you can calculate it using this equation. So here's the properties. As the ionic strength goes to 0, the gamma goes to 1, the activity of that ion in solution goes to its normal concentration value, and this thermodynamic equilibrium constant approaches the concentration equilibrium constant. And for mu much greater than 0.1 molar, this gamma depends mostly on mu. Okay, it depends greatly upon z. It's again 10 to the minus z squared. And for a given mu, gamma is the same for ions with similar charge densities. So we can look those up in those tables. If they have the same hydrodynamic radius, then they're going to have similar activity coefficients. And then the gamma for a given ion will describe its effective behavior in all of the different equilibria. So sodium ion in water is going to affect all of these equilibria at the same ionic strength. So we talked a little bit about this. I showed some examples, some really crazy, seemingly absurd examples that this alpha I, it says alpha X in this text, so this is alpha I from previous pages. These are gamma I's right here in the table. Okay. And these numbers right here are mu. So you calculate ionic strength first. Then you find your ion in this table. This tells you alpha. And then if you are at one of these, if you happen to be lucky and you are at one of these ionic strengths, you can just read off the gamma for that ionic strength. Okay, that's nice. If you're not at one of these columns, then you have to interpolate between the columns or just use the debye-hukel equation. It'll give you the same answer. But yeah, this is kind of a strange situation. You have this benzoic acid, and we're saying that behaves the same in water as lithium ion, which is really bizarre. They're opposite charges. This has got, let's see, you've got 14 atoms in this one, and this is a tiny little second row cation. Yet they have the same water entourage and organizational properties in water. There's some other really weird ones too. Here's phthalate. Again, that's a benzoic acid, a diacid. It's got 2 carboxylic acids on it. It's behaving like all of these 2+ ions. Here's ferrocyanide, 3- and phosphate 3-. So you see the major effect is the charge. Here's thorium, zirconium, cerium, tin, 4+, etc. So there's some also funny things in terms of which ones are large and which ones are small. But again, the larger the charge, you see 0.9 here, huge entourage. But these, again, I would have lost this bet that phosphate. I would think phosphate would be larger or the same as 3+, but it's coming in at smaller, like half the size. So, what can I say? But in general, the larger the charge, the larger the effect. So here's some calculations. So what's the activity coefficient for mercury 2+ in a solution that has an ionic strength of 0.085? So we've already calculated the ionic strength. We know mercury. So the 2+ here goes in for Z. We look that up in the table. We find the 0.5 from the table. The ionic strength of 0.085 goes in here, and then it's plug and chug. We have everything we need in the problem. Don't forget to change the sign here, and don't forget to raise it, 10 to that power. And don't forget to add in this 1 before you do the ratio. That's a common mistake as well. So we end up with 0.4. If you wanted to use the interpolation method, here's mercury down here, mercury 2 plus. Okay, we are at 0.85. So we're, between 0.05 and 0.1. So we start out with this smallest piece of 0.46 that goes right here. And then how far over to 0.1 are we? Well, we're 0.085 minus 0.05. This is how you interpolate. How far am I over to the right column? That difference is how far I've moved towards the right column. And then this is the slope. Okay, this is 0.38 is the right column's value for gamma. 0.46, so this is essentially M. This is X, and this is B. So that's a linear interpolation. That's how you do these. And so this would be essentially rise over run here. That's the slope. And that'll give you the 0.4. So this is how you interpolate in a table. Now, is it a linear effect? No, it's not, because you have this 10 to the x and all of these different exponents. But they give you tables, and for that tiny little difference, it doesn't matter if it's really a curved thing, but you can assume, as long as your data points are close together, you can assume it's linear between those two columns. So that's what we're doing. We're taking some strange curve, and we're just saying it's a linear interpolation, drawing a line between these two known points. And we're going to be off, but only by a little bit. So then I show some examples, and you can, again, go through them in slow motion or real time in the video that's on Blackboard. But I just wanted to walk you through. We do an ICE table with the activity coefficients. Notice that we have the activity coefficients here in front of our concentrations here. So we have the activity coefficient for barium to correct the barium concentration, and the activity coefficient for iodate to correct that one. So including our activity coefficients, here's the solubility of the barium. So 1.56 times 10 to the minus 6 molar. If we did it without, let's see, where do we do it without? Here we did it without on this side right here. 0.36 times 10 to the minus 6. So you see, this was what, if we don't take into account ionic strength, we would say this is the solubility, 3.6 times 10 to the minus 7. I put them on the same power of 10 so we could compare them. So we would have estimated at 0.36, the actual would be 1.5 that, so 5 times more, which is pretty impressive error. We're 77% wrong. It's not great. Okay, so that's why we need to take into account activity coefficients. There's other kinds of equilibria that we do, like acid-base chemistry. Here would be the concentration of hydronium ion without the activity coefficients. And so that would give us a pH of 2.1. If we take into account activity coefficients, we end up with 2.03. So it's not quite as acidic. Okay. What about titrations? So we'll skip ahead. We've got these buffer regions, and I just want to show you this last piece that if we take into account ionic strength of a buffer solution with all of those concentrations of ions, this ionic strength is off the charts. And literally, like if you go to the analytical chemistry book to try to find the ionic strength, activity coefficients, it's off the table. It's off the charts for real. So what do? Well, most of the time when we make up buffer solutions, we don't calculate the theoretical pH. We stick a probe in there and adjust it with a little bit of acid or a little bit of base until it's the pH we want. So we pick an acid-base pair that's going to give us the pKa that we want, and so the buffered pH is centered around the pKa, which is halfway to the endpoint. Notice in this buffer region, I'm adding a ton of concentrated base, but the pH is only going up a little bit. So that's what buffering is. And so if we want a buffer, we pick a acid-base pair that has the pKa that we want, and then we adjust the pH. Like say we have one that's going to give us a pH of 4.2, and we want a 4.5 buffer. We would just add a little bit more base and move it to 4.5, then we've made a 4.5 buffer. And that's how we really do it. But if you wanted to calculate the theoretical values, you'd have to get in there and calculate the ionic strength, the hydrodynamic radii for all the ions, and then calculate the activity coefficients. And it'll be quite tedious. Okay. So those are the main points of the aqueous equilibrium.